forward to this. Okay, so we're going to continue on with chapter 19. We're just introduced the concept of the Claisen reaction. And the Claisen reaction was exclusively for an ester, and it required at least one of the esters in the system to have the alpha hydrogens that can be deprotonated. And then we had 4 different varieties. We could have where you used 2 equivalents of the same ester, and that reacted a certain way. You can have a compound with 2 esters on it, and it forms a ring. That's one way. We can make the enolate out of an ester and attack an acyl halide to generate that product. Or we can take an ester with a alpha hydrogen and an ester without an alpha hydrogen and generate another Claisen product. And the key in all the Claisen products is you have the the beta keto ester is the form there. Notice in the previous reactions, we hydrolyzed and decarbonylated. You still can do those at the end of these reactions, but the key is the Claisen will always give you that keto ester as your initial product. You can do other reactions on it, but all of the Claisens you'll see will do that. Okay, so that's the defining thing about the Claisen is it's forming an enolate with an ester, and at least one of the substrates have to have alpha hydrogens to do it. Now, we're going to move on to another named reaction, but it basically has the same mechanism. It's just we end up with a different product because we're starting with a different place. Okay, so the next reaction I want to talk about is called the Aldol addition, and it's occasionally called the Aldol condensation as well, because we do actually extrude some things sometimes, but the point of it is this is typically called the Aldol addition because we end up stopping at the carbonyl alcohol, the beta hydroxy carbonyl compound. Okay, and we'll talk about that. Okay, so just like in the Claisen condensation, our first step is the same. We deprotonate an alpha hydrogen. That alpha hydrogen, once removed, now our carbon is our nucleophile, and it attacks another carbonyl species. And when it does this, it doesn't have as good a leaving group. And so instead of going back to our carbonyl compound through an elimination or a condensate product, we typically, the first step is to generate an addition product, or we have a tetrahedral center. So we're going to have that beta hydroxy compound is formed from that. Now, that does not necessarily mean that's the final product, but this is the intermediate we form, is this addition product to give us our tetrahedral center. Okay, so that's the key feature that's very different from the previous reaction, is we can isolate it at this tetrahedral center intermediate. Okay, so let's talk about the mechanism a little bit. Okay, so just like in the other reaction where we have an alpha hydrogen, we deprotonate that alpha hydrogen and we generate our enolate. Our enolate then acts as a nucleophile and attacks some other carbonyl compound. Okay, so everything up to now is about the same mechanism as we saw before, and we stop at this part right here. Okay, so at this point, the only thing that we can do is to reprotonate the material right here, and we end up with our beta hydroxy, in this case aldehyde. It's either an aldehyde or a ketone. Okay, so that is the final neutral product after the reaction is quenched with water. Okay. So notice here, we did not reform our carbonyl. We did not have something extrude out and condense. Therefore, it's the Aldol addition reaction. Okay, and we've generated this tetrahedral center from our previous trigonal planar carbonyl compound. Okay, so now we can do this with aldehydes or ketones. If you have an aldehyde, you only have one set of alpha hydrogens, so your product is controlled by those one set of alpha hydrogens. In the case of ketones, ketones react more slowly because of sterics, plus you have to compare the acidity of the two sides of your ketone. One side might be more acidic than the other, or it could be about the same. You'll get a mixture of products. So ketones react a little bit slower to sterics, and you have selectivity issues that you don't have with the aldehydes. So the aldehyde has a really good selectivity because it only has one set of alpha hydrogens. Okay. Now, let's go through the differences between the aldol and the Claisen. Okay. The aldol always uses an aldehyde or ketone as a substrate. Okay. The Claisen always uses an ester as a substrate. In both cases of the aldol and the Claisen, you must have alpha hydrogens. Okay. So that is important right here. The big difference between the two is in that last step. After you form that intermediate with that tetrahedral intermediate here, you can, in the Claisen, you have a good leaving group. You have the alkoxide as a good leaving group, a heteroatom as a good leaving group. In the Aldol addition, you only have a hydride or a carbanion as your leaving group. Those are really, really strong bases, and therefore it's very difficult to regenerate the carbonyl compound. Therefore, you end up with your beta hydroxy carbonyl compound. Okay, so let's pull this up at the bottom and blow it up again. Okay, the Claisen has that alkoxy as a leaving group. Okay, it's a strong base, but it's still a pretty decent leaving group. The aldol has only the hydride or the carbanion as a leaving group. Therefore, it does not want to leave, and it stops at that addition product. Okay. So before, when we had the Claisen, we could have two different esters and make a different product. We can do the same thing with the aldol condensation, and we do that for a nice specificity, and we do the same rule, okay? We do the same rule because you have one substrate with no alpha hydrogens and one substrate with alpha hydrogens, and you have very selective product that only form one thing, okay? Now, in the case of an aldol condensation, if we take our compound here and start to deprotonate it and then react it, we actually can end up with 4 products depending on which carbonyl compound we end up with and which enolate we form first and whatever. If we reacted it with itself, we can end up with 4 products. Okay, and I believe that's in a homework problem too, so you can see that. So by using selectivity of having one substrate have the alpha hydrogens and the other straight not having the alpha hydrogen, you only get one product, okay? So in the case of our substrate here, let's go to the red ink here. This one has alpha hydrogens, so you're gonna form your enolate from here. This one has no alpha hydrogens, so that enolate must attack here, okay? So a key feature in this aldol condensation is the compound that formed the enolate keeps its carbonyl compound, okay? So this one formed that. The other carbonyl that had no alpha hydrogens is the one that turns into the alcohol, okay? So when you're starting to look at these compounds and say, how did I make that? Okay, the one with the alcohol is the one that got attacked by the enolate. The one with the carbonyl compound, either the aldehyde or ketone, still intact, is the one that was the enolate. Okay. So most of the times you can actually just stop the reaction at this stage here. However, with heat or acid, you can actually do a dehydration reaction to form an alkene. Okay, and I'll talk about that on the next slide. Okay, so when we look at a crossed aldol condensation, one compound has alpha hydrogens, that's the one that makes the enolate. The other compound has no alpha hydrogens, that's the one that ends up making the alcohol portion of our aldol. Now, can we do the same thing we did with the Claisen and make a ring? Well, oh, sorry. Second rule in the mixed one right here. is that we can actually help the reaction by using an irreversible base. Okay, so if we use LDA, LDA is that irreversible base. It forms that anion, that enolate anion, and then it doesn't allow it to equilibrate, right? So we can form that anion. And so if we have one substrate and we add our irreversible base to it, and then we wait until all of that substrate has had those protons removed, then we slowly add our second aldehyde or ketone, we can get our crossed aldol product selectively using where we only have, we've used it to deprotonate only one of the two species. And then by slowly adding this, this is going to slowly react with the aldehyde or ketone you add to it to give a selective product, okay? Again, the one you added first is going to give your enolate and will always have the carbonyl compound on it. The second one you add is the one that's attacked and will always have the OH on it. So if you looked at this product and knew it was an aldol condensation, you would know that this would have to have been the aldehyde or ketone that was added to the system, and this is the one that you made the enolate from because it maintained the carbonyl compound. Okay, now we're doing rings? No. All right. So there's a modification that we can also do, is that you can do that same thing where you make the material and you can react an aldehyde, I'm sorry, the ketone with an ester. So this is like the difference. This is not an aldol and it's not a Claisen, it's a mixture of the two. Okay, so we take an aldehyde or ketone with alpha hydrogens. And because there's no electron donating group nearby, and in this case, the electron donating group is this, that makes these hydrogens more acidic than these hydrogens. Okay, so in the case of this mixture, we're using electronics of this donating group to say, I'm only going to make the enolate out of the ketone, and therefore the ketone is the one that's going to react with the ester. Now, when that ketone reacts with the ester, we have a good leaving group in that alkoxide ion, and therefore we end up generating our beta diketone compound. Okay. We can also use an aldehyde ester, and it actually makes a nice compound where we can make this beta keto aldehyde. And so the aldehyde's at the end, because again, this is going to be the most acidic hydrogen here. There are no alpha hydrogens on this compound at all. It's going to come in here and attack your carbonyl carbon and then spit out our ethanol, or in this case, the alkoxide ion, and regenerate our carbonyl to give us our beta keto aldehyde. Okay, so compounds with, you can react an aldehyde or ketone with alpha hydrogens and one or more of itself and end up with multiple products. You can do a crossed aldol where you have one compound having alpha hydrogens and the other compound not having alpha hydrogens, and that gives you a very clean product, and it always gives you the carbonyl beta hydroxy compound. If we react it with an aldehyde and ketone and an ester, the aldehyde or ketone has the more acidic hydrogens and therefore can generate a beta ketone or a keto aldehyde compound, depending on which ester you start with. Okay, so now, just like with the Dieckmann, we can actually do a reaction of the aldol condensation or aldol addition within the molecule. Okay, and that's the intramolecular aldol. Okay. So if you have a diketone compound or a dialdehyde compound, you can form ring structures from the system. But just like with the Dieckmann cyclization, the intramolecular aldol condensation, you will only form 5 and 6 membered rings. Okay, so you're only going to form 5 and 6 membered rings. However, where you form the enolate will change whether it's a 5 or 6 membered ring. Let me show you. Okay, in this case here, we have this diketone species right here, and we have two different types of acidic hydrogens, right? We have alpha hydrogens here, and we have alpha hydrogens here, okay? They're both about the same acidity because they're both right near carbonyls, and it's not like there's a diketone where you have two ketones pulling on the same carbon, making it very acidic. They're about the same acidity, okay? So we have two choices. We could actually pull the alpha hydrogens off here, and if we did that, that generates this intermediate here. We have the enolate ion on the terminal carbon, which can then come in and react with the other carbonyl compound, and that would give us a 5-membered ring. And of course, when we protonate it, we end up with our beta hydroxy ketone compound. Okay. What if instead we formed the enolate with the internal one here? If we actually had attacked by that one, we would end up attacking this carbonyl compound, which gives us a total of 3 carbons in our ring. That 3-carbon ring is way too strained. It will not form, and we will not get the product from this internal deprotonation of the dicarbonyl, of the diketone, only the external deprotonation of the diketone. Okay. So if we had a longer chain in the middle, we can actually deprotonate those inner ones and still form a 5 or 6-membered ring. So let's take a longer one here. This is a 1,6 diketone compound, meaning we have 4 CH2s in between the 2 carbonyls. When we do that, if we deprotonate the external alpha hydrogens here, and it comes in and reacts with the carbonyl, we're going to end up with this 7-membered ring, okay? 7-membered ring, that's a little too disordered. There's too much entropy, and we actually don't form it because that is too disordered. However, if we do deprotonate at this internal CH2, those acidic alpha hydrogens here, that when it comes in and attacks the carbonyl, generates a 5-membered ring, and we end up with our beta hydroxy carbonyl compound right here. So just like in the intramolecular Claisen condensation, you're looking for 5- and 6-membered rings as primary products, not 7-membered or 3-membered or 4-membered rings. Okay. Questions on that? This is, again, going to be part of our activity on Thursday. But with all of these, the mechanism to get to that tetrahedral intermediate is exactly the same. The only difference is in the aldol condensation, we don't have a good leaving group, and therefore it stops at the alcohol. It does not regenerate the carbonyl compound. Okay. But I said the reaction stops at the alcohol. So you actually generate the beta hydroxy carbonyl compound at the end of the aldol addition reaction, okay? However, if you take that hydroxy compound in the presence of acid and heat it, what can happen is you can do a acid catalyzed dehydration to form a double bond, a carbon-carbon double bond. And the reason this happens quite readily is the fact that when you form this double bond, it's actually in conjugation with the carbonyl compound, okay? So a lot of times if you have your your aldol condensation reaction, you have step 1, base reaction, step 2, heat and acid. So that turns it in from the aldol addition reaction to the aldol condensation reaction, because you end up liberating water. You lose water, you condense water in your system, okay? So you can also do this with heat in a base catalyzed dehydration, but it's a slightly different mechanism. Okay. So when you're looking at an aldol addition product, there's no heat present. If you're going to dehydrate the material and get a alpha beta unsaturated aldehyde or ketone, a conjugated unsaturated aldehyde or ketone, you will have to add heat in that final step. Okay. No, I don't think we want to talk about that. Okay, so what I want to do right now is I want to summarize the reactions we just did and start talking about them as, there we go. Okay, great. There we go. So we have 4 different types of reactions we have here, but they all start with the same step in the mechanism, okay? The first step is you have to have those alpha hydrogens. Once you remove one of those alpha hydrogens, you now made a nucleophile. And we see that we can do addition reactions to give us our tetrahedral center. We can do acyl substitution reactions to give us different materials. We can then also regenerate carbonyl compounds, like in the presence in the Claisen reaction by having a good leaving group, or we can end up with our tetrahedral center if we don't have a leaving group, like in our Claisen. So I think it's important that maybe you go and look at the starting material and product and starting material and product and starting material and product and start organizing both chapter 18 and 19 together in that way. I'm going to go ahead and build my own table, and I'll actually distribute that tonight or tomorrow, and we'll see if my table and your table kind of line up. Okay. The cool thing is that pretty much, you know, we add bases to these things, we deprotonate our alpha hydrogens, but they do different things, and by adding the other substrate to it, you end up with different products. So we need to start looking at starting material and product and assigning like the type of reaction it is from that. All right, any questions on that? We're just a little under time, but I really want to save a little bit for tomorrow and go ahead and work on this table. And I think if you devote some time to working on that table, it'd be really helpful in kind of defining these 2 chapters together. Okay, I'm going to stop recording.